Okay, today we're going to look at section 711, expected value. And we'll start back with gambling. Casino game roulette has dozens of different bets that can be made. These bets have different probabilities of winning, but also have different payouts. In general, the lower the probability of winning a bet is, the more money a player wins for that bet. With so many options, is there one bet that's smarter than the rest? What's the best play to make at a roulette table? In this section, we'll develop the tools we need to answer this question. So what is expected value? Many experiments have numbers associated with their outcomes. Some are easy to define. If you roll 2 dice, the sum of the numbers showing is a good example. In some card games, dice have different point values associated with them. For example, in some forms of the game Rummy, aces are worth 15 points, tens, jacks, queens, and kings are worth 10, and all other cards are worth 5. The outcomes of casino and lottery games are all associated with an amount of money won or lost. These outcome values are used to find the expected value of an experiment, the mean of the values associated with the outcomes that we would observe over a large number of repetitions of the experiments. You can see your conditional probability and multiplication rule for more on means. What we're talking about is if you played 1,000,000 times, this would be what you would expected to win on average, the mean. So how many is a large number? Well, in practice, it depends on the experiment. Number has to be large enough that every outcome would be expected to appear at least a few times. For example, if we're talking about rolling a standard 6-sided die, and we note the number showing, a few dozen replications should be enough that the mean would be representative. Since the probability of each outcome is 1/6, we could expect to see each outcome about 8 times over the course of 48 replications. However, if we're talking about the Powerball lottery, where the probability of winning the jackpot is about 1 in 292 million, we would need several billion replications to ensure that every outcome appears a few times. Luckily, we can find a theoretical expected value before we even run the experiment the first time. The expected value, if O represents an outcome of an experiment, and N of O represents the value of that outcome, then the expected value of the experiment is the sum of all of the values of the outcome times the probability of the outcome. So let's find the expected value of the number showing when you roll a 6-sided die. So let's see what we have here. What are our possibilities? 6-sided die with the faces 1, 1, 2, 3, 5, or 8. So these are all our outcomes. So how many times would we get the 1? It's in here 2 times. So the probability of that would be 2/6. Probability of the 2 would be 1/6. Same with the 3, same with a 5, and same with an 8. So now we take the roll, and this is the probability, and then we multiply them. So we have the roll times the probability. So this would be 2/6. This would be 2/6 as well. This would be 3/6. This would be 5/6, and this would be 8/6. So our total here would be 20/6 or 10/3 or approximately 3.33. Okay. Find the expected value of the number of heads showing if you flip a coin 3 times. So we have the number of heads. It could be 0, 1, 2, or 3. So how many different ways can we do this? Well, this is small enough we could write it down. Head, head, head. Head, head, tails. Head, tail, heads. Tail, head, heads. Head, tail, tail. Tail, head, tail. Head, tail, tail. And lastly, tail, tail, tail. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 possible outcomes. So 0 heads. 1 out of 8. 1 head. Here's 1 head. Here's 2 heads. 1 head. Here's 1 head. 3 out of 8. 2 heads. Here's 1, 2, and 3. 3 out of 8 as well. And then 3 heads, 1 out of 8. Notice adding this, we get 1. So now I take the number of heads times the probability and get 0, 3 eighths, 6 eighths, and 3 eighths, which gives me 12 eighths or 1.5. Okay. Okay. So you are about to play a game where you flip a coin 3 times. So we can go from the previous example. 1 eighth, 3 eighths, 3 eighths, and 1 eighth. If all 3 flips result in heads, you win $20. If you get 2 heads, you win $10. If you flip 1 or 0 heads, you win nothing. So now I take my probability times my winning. 0, 0, 30 over 8, 20 over 8. We get 50 over 8, which is 6.25. What is the expected value of your winnings? $6.25. Okay, so the expected value of an experiment is the mean of the values we would observe if we repeated the experiment a large number of times. This interpretation is due to an important theorem in the theory of probability called the law of large number. So let's use this to interpret the results of the previous example. So interpret the expected value of the number showing when you roll a special 6-sided die with the faces 1, 1, 2, 3, 5, 8. So if you roll the die many times, the mean of the number showing will be, and if you recall from that example, it was 3.33. Okay, interpret the expected value of the number of heads showing if you flip a coin 3 times. If you flip a coin 3 times, many times, the mean number of heads would be 1.5. And lastly, interpret the expected value of your winnings If you play the game many times, your average, well, your mean winnings will be $6.25. So using expected value, how can we use this? What will it do for us? And now that we know how to find and interpret expected values, you can turn our attention to using them. Suppose someone offers to play a game with you. If you roll a die and get a 6, you get $10. However, you get a 5 or below, you lose $1. Is this a game you'd want to play? Let's look at the expected value. The probability of winning is 1/6, and the probability of losing is 5/6. So the expected value is 10 times 1/6 plus -1 times 5/6, which would be about 5/6 or 83 cents. That means on average, you'll come out ahead by about 83 cents every time you play the game. It's a great deal. On the other hand, if the winnings for rolling a 6 drop to $3, the expected value becomes 3 times 1/6 plus -1 times 5/6, which would be minus 1/3 or negative 33 cents, meaning you'd lose 33 cents on average for every time you play. Playing this game is not a good idea. In general, this is how casinos and lottery corporations make money. Every game has a negative expected value for the player. So let's look at an example of this. The casino game Craps involves rolling 2 standard 6-sided die. While the main game involves repeated rolls of the dice, players can also bet on the outcomes of single roll. Find the expected values of the following 3 $1 bets. Then decide which bet is the best for the player and which bet is the best for the casino. So here are 2 die, and these are our outcomes. It just seems easier to do this table than to think about it too hard. So these are our outcomes. And there are 36 possible outcomes. So players can bet on the next roll of the dice being a sum of 7. Winners get $4, losers lose $1. So how many 7s do we have? There's 6 of them. So the odds of winning are 6 over 36. Times our winnings, 4 plus -1 times the odds of losing, 30 over 36. So we have 24 over 36 minus 30 over 36, which is -6 over 36, which is approximately minus 17 cents. Not the best of cases. Players can bet on the next roll of the dice being the sum of 12. Well, there's only one of those. Winners get $30, losers lose $1. So we have 30 times 1 over 36 plus -1 times 35 over 36, which is 30 over 36 minus 35 over 36, -5 over 36, which is roughly -14 cents. So a little bit better. And next we have players can bet the next roll of the dice will be any craps. which is 2, 3, or 12. So 4 of 36. And you get $7. Plus -1 times 32 over 36. You get 28 over 36 minus 32 over 36. -4 over 36, which is approximately -0.11 or 11 cents. So this is best for player. Player loses the least. This is best for casino. Note that in all three cases, the bettor is expected to lose, which is how casinos get all those expensive bright lights. And that finishes expected value. And that finishes our probability chapter.